last time we discussed taking the derivative of some types of functions, right? So power functions, we're pretty okay with, right? Things that look like x raised to a power, right? I know that the derivative is going to turn those into something like this, right? Where the exponent becomes a coefficient, and then the exponent is reduced by 1. And I also know a couple of other things about taking the derivatives about how functions are kind of put together. Right? I know that the derivative of a constant is 0 if you take its derivative. And linear functions really fit into this kind of power function thing, right? But they're worth noting, I guess. So if I had something like just a number times x, this is really x to the first power. So this is just going to be a. 1 minus 1 is 0, so this is x to the 0 here. And anything to the 0 power is 1, except for 0 to the 0 power, which is undefined. We talked about constant multiples. Okay. So if I know what to do with f of x, and I'm multiplying it just by some number, I'm okay, because that number is just going to stick around. And I'll just take the derivative of the function. Okay. We saw it work here with linear functions. It works in general. Right? If you have a number, and it's just some number, it doesn't have any x's in it, it doesn't have a variable in it, that constant multiple will be found in the derivative as well. So you can just kind of ignore it for a little while and deal with what's changing, because the derivative is all about change. We also talked about sums and differences. So if I have two functions that are being added together, and I want to take their derivative, I can just take the derivative of the first one, and then the derivative of the second, and add those together. It works exactly like we would want it to. Differences are similar because differences are just this put together with constant multiples. Right? You may think of subtraction as adding the negative of the next function, right? Plus negative 1 times. Okay? So just to formalize it, f of x minus g of x gets turned into f prime minus g prime. Right? I can just take the derivative of each thing. All of this together is going to allow me to do polynomials, but also much more. Simple roots. We saw in the homework where we might have more complicated expressions that might simplify down to something that we can take care of. Right? So like x times the quantity root x plus 1, all divided by root x, right? Has multiplication and division going on in it, and there are roots. But if I try to simplify it, I can simplify it down to just where it's a constant times x to a power, plus a constant times x to a power. So those types of things work really well here. But there are more functions than just power functions. For instance, anybody have a favorite function that is not a power function? Well, I mean, constant multiples will be a number of times, right? Yeah, so a constant multiple is something like 2 times x squared. This 2 is being multiplied by x squared. So x squared I know how to take the derivative of. 2, I don't. Or we're not going to be talking about trigonometry in this section. But say, for instance, the trigonometric function sine of x, its derivative is cosine of x. You don't have to know that. But if you did know it, I would know that 2 sine of x would get turned into 2 cosine of x. This constant coefficient is just going to be part of the derivative also. Yes?
And how would you be able to differentiate that 2 times x squared from 2x squared?
So 2x squared from this?
Yeah. Or, I mean, what if the square was in parentheses?
If the square were in the parentheses, I wouldn't need the parentheses, right? I would just write it 2 times x squared.
So that is the difference.
Yeah. So here, 2x squared is 2 times the quantity x squared. The order of operations that we just kind of have all kind of agreed to as a language that we're going to use is telling me that this exponent is going to happen first, and then I'm going to multiply by 2. Whereas here, I have this parenthetical expression, and all of it is being raised to the second power. So I'm going to multiply by 2 and then square the result. It turns out that we have ways to kind of move between these types of things, and 2x squared is actually the same thing as 2 squared x squared, which is 4x squared. Okay. So if I saw this and was asked to take a derivative, it's a composite function. I have a function shoved inside of another function, and I don't know what to do. Right? That's not something I'm at this moment prepared for. But I could simplify it to 4 times x squared, and now it's an equivalent expression that I am prepared for. Does that make sense? And right now, that's kind of like our toolbox, right? I have one type of screwdriver, and if I can't use that screwdriver, I don't know what to do. So I'm just going to try to make all of my screws look the same so that I can do the job. Okay. As we kind of move through this chapter, we're going to discover more methods, better methods to be able to kind of approach different types of situations, right? So if I have a composite function, is there a way for me to address the issue now instead of having to write it a different way? Or if I have a product or if I have a quotient, are there things that I can do in order to address those issues in situ, right? The way that they are now, instead of having to force everything down to this previous case. Because if I start throwing other functions in there, I might not be able to simplify them quite so easily. Okay? So here's a trigonometric function, right? Sine of x, I know that it gets turned into cosine of x, but if I had something like sine of x squared, there's no better way for me to write this. I have a function inside of a function, and this is as good as it gets. I can't write it just in terms of sine of x or just in terms of x squared. Kind of hosed. Not that we'll be talking about sine of x explicitly, but it's an example of a function, and this would be a problem that might arise, which is going to necessitate some of these tools that we'll be talking about. So sine of x is an example of a function that's not just one of these power functions or a multiple of it. Okay? But sine of x is one that we won't be discussing. Anybody familiar with a type of function that we might want to discuss? Yeah.
Would that be like f of g of x?
So f of g of x for us right now, so it would be a composite function, right? F of g of x. I don't know. But if we stick to the examples that we have been doing, for polynomials, this won't cause us a lot of problems. Right? So if, for instance, I had f of x equals x squared plus 2x plus 1, and g of x was equal to 3x plus 4, I could stick g into f like so. And this looks complicated, but once I evaluate, I could simplify this back to a place that I like. Right? It's going to be 9x squared plus 24 plus 16 plus 6x plus 8 plus 1. Right? I'll be able to multiply everything out, and it'll simplify down to something that I like. I'm talking about something that's a completely different animal from just things that look like polynomials or power functions, x raised to a power. What other functions exist out there? What other things can you do with numbers aside from just raising them to a power? This way.
Take the natural log of those functions.
Absolutely. So there's an example of a function. Right? Okay. So what about the natural log? Any other functions? Natural log of x is tied to another function in particular. Yeah, logs in general, right? So log base anything. I thought I heard it whispered in fear out there. Yeah, right? E to the x, this is exponential function, is a type of function that is out there that's not x raised to a power. Right? This is kind of the opposite of that, right? Before we had x raised to a number, this is a number raised to the x power. Right? So before, the base was changing and the exponent was always the same. Now the base is staying the same and the exponent is changing as x changes. So this is tied to the natural log of x. They're inverse functions. So this, I don't know how to do either. Things like 2 to the x or 3 to the x. Right? Any number to the x, I'm not really sure about its derivative. These are called exponential functions. We're going to kind of talk about exponential functions, and then we'll try to get to logarithms kind of through the back door, right? I don't want to tackle logarithms like head on. I'm going to talk about exponential functions, and then once we have a good understanding of exponential functions, we'll kind of introduce ourselves to logarithms through exponentials. That's familiar with the way that we've talked about logarithms before, right? If I think about things like log base 2 of 8, right? Log base 2 of 8. I'm thinking 2 to what power equals 8? Right? Exponential expressions are expressions that we're familiar with, and logarithms are the inverse of that exponential operation. And so thinking about logarithms in terms of exponents makes them easier to solve, easier to evaluate, wrap our heads around. And so that was the way that we were introduced to logarithms to begin with. And so it's only natural that for derivatives that we first contemplate exponential functions and then kind of come back to worry about the derivatives of logarithms once we're familiar with exponential functions because we like them better. So let's look at exponential functions in general. Right? I've got some number a, and it's raised to the xth power. And so if I want to know its derivative, I'm going to have to be concerned with the limit of this difference quotient, right? By definition, this is what the derivative of a to the x is, right? You plug in x plus h, and then you leave it alone, right? You find how different the expression got when you added h to the x's, and then you divide that by the change in x's, which we just defined to be h, and you see what happens as that change in x's shrinks to nothing. Right? This is the slope of a secant line as you kind of push the points closer and closer and closer together so that there's no difference between them, and you get a tangent line. Right? So just by definition, this is what the derivative is. And I need to be able to kind of manipulate this so that maybe I can get rid of this h. That was our thinking before, right? I don't like that I'm dividing by 0, just plugging this in. If I just plugged 0 in for h, I would get 0 over 0, which I'm not a big fan of. Right? 0 over 0 is indeterminate to me. So I need to kind of finesse this to try to make it look a little bit different. I'm adding these exponents, and I happen to know that in terms of exponential operations like this, when you multiply two expressions that have the same base, right, a to the x times a to the h, what you get is a to the x plus h, right? Sums of exponents happen because you're multiplying two expressions of the same base. Are we familiar with this rule? Don't lie to me, everybody's good, right? If I had something, we'll have a little Shakespearean aside over here, right? If I had something like x squared times x cubed, everybody would be comfortable saying that was x to the fifth, right? What's happened is that you've recognized that x and x have the same base, and we're multiplying, so we can say 2 plus 3, which is fine. I'm just doing that backwards, right? Which we might have done if we were factoring, right? If I had something like x to the fifth plus x cubed, I might think of this x to the fifth as x squared times x cubed. So I can see that there's a factor of x cubed hidden away inside of this x to the fifth. So if I pull an x cubed out, I can see that x cubed is a common factor in both of those terms, and so I get x cubed times x squared plus 1. This relationship for exponents is exactly what we're trying to exploit here to get that h by itself. Okay? The rest of this expression is just going to stay the same. But what I've been able to accomplish is there's an a to the x that's a factor here, and an a to the x that's a factor here. And because I have this common factor in each of those terms, I can just yank it out. This has an a to the x, and this has an a to the x, so I'm going to factor that a to the x out. And if I remove this factor of a to the x, I'm going to be left with a to the h. And if I remove the second factor of a to the x, I'm going to be left with 1. It's got this 1 coefficient just kind of hiding there. And it's all over h. This a to the x is a factor of the entire expression now, right? This is a to the x times everything else. And this a to the x has nothing to do with h, right? H could change all day. A to the x would still be a to the x. So I'm just going to think about it on the outside here. So really, this limit is the same thing as a to the x times whatever this limit is. The limit of a to the h minus 1, all divided by h. And what's fascinating about this, what's exciting to me about this, is that this limit is just going to be a number. It doesn't have any x's in it. It's not a function, right? X can be whatever you want, and this is just going to be the same thing, right? H is changing, and this doesn't have any x's in it whatsoever. So if this limit exists, it's just going to be a number. That's awesome. Right? That tells me that the derivative of a to the x is just a to the x times some number. And that number is going to depend on what a was. Yes?
So if they don't tell us what A is, we can't determine what that number would be?
Not exactly. That number is going to depend on a. It's going to depend on whatever the base was, right? But this is kind of exciting, right? It looks almost exactly the same, right? The derivative of a to the x is a to the x times some number, right? The derivative of x squared wasn't that way. The derivative of x to the fifth or the square root of x wasn't that way. They changed, right? X squared became 2x. It's not x squared anymore. But 2 to the x is still going to be 2 to the x times some number. So our thinking is that 2 to the x, when we take its derivative, is 2 to the x times some number. And the derivative of 3 to the x is going to be 3 to the x times some number, some different number. That says different, some different number, right? And the derivative of everybody's favorite, e to the x, right? This is 2.718281828, blah, 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 right? Is just going to be e to the x times some number depends on e, right? E is going to determine what number this is. 3 determines what number this is, and 2 determines what number this is. But they all look almost exactly the same. It's just you got to tweak the final function just a little bit by multiplying by some real number. And now there's a fun mystery, right? There might be some number out there where that some number that depends on the base is just 1. And then the function would just be its own derivative, right? There's some a out there, right, where it's a to the x, and it goes to a to the x times 1, which is just a to the x, for some number. Right? There's some number a out there so that a to the x, you take its derivative, it's just a to the x. And that a is this one, where the limit as h approaches 0 of a to the h minus 1 all over h is 1. Okay? So there's some special number a out there so that this limit is 1. And that would mean that we got a to the x times 1, which is just a to the x. Everyone just burning with curiosity right now? A little excited? There's some magic number out there for which this is true. It's kind of neat. I'm going to spoil it for you. E is that number. That's what's special about E. Okay? You may have been wondering for ages now what the hell is so special about 2.718, etc. That it gets its own letter, and other numbers don't get their own letter. Right? Not every number has a letter. E has a letter. It has its own button on most calculators now, right? What's special about it? This is one of the things that's special about it, right? It's the number that this is true for. Okay? So the derivative of e to the x is e to the x. This is what goes in the box. This is the first exponential expression that we are going to be really concerned with. We'll get the rest of them once we kind of figure some stuff out. But this one's first. The derivative of e to the x is just e to the x. It's the world's simplest derivative. There is only one other function whose derivative is itself. Anybody think of it? We already know it. 0. Yeah, the derivative of 0 is 0. So the derivative of 0 is just 0, and the derivative of e to the x is just e to the x. Those are the only two out there. All other functions in the world, their derivatives change from themselves. But not e to the x and not 0. Cool, yeah? Maybe, sort of. So this opens up some new types of function for us. We can now consider things like this. f of x is x squared plus 3x minus e to the x. Or g of x equals 4 e to the x plus the square root of e to the x. And what's the derivative of f here? I'm hearing it from several sources here. Seems pretty good, right? Because I'm just adding these terms together, I can just take each term in order. And so x squared is 2x, 3x is 3, e to the x is e to the x. What about g prime if g is 4 e to the x plus the square root of x? Yeah, right? 4 e to the x, this constant coefficient doesn't mean anything, right? The derivative just leaves it alone. E to the x, its derivative is e to the x. And then root x, remember we're thinking of root x as x to the 1/2. So I can treat it just like any other power function. The 1/2 becomes a coefficient, and I subtract 1 from the exponent. Now, don't write this down, but someone in here is going to make the following mistake this semester. Do not let it be you. They're going to see e to the x, and they are just going to blindly say that the derivative is x e to the x minus 1. Okay. You just bring the exponent down and you subtract 1. Okay. But that's not true, right? No. Please don't. Okay. I don't want to do that. These are two different types of function. Okay? X raised to a number, right? These functions change differently than some number raised to the x. Okay? They're different types of function. These kind of create curves that look like one of these two in general, right? X raised to an even power, right? X squared, x to the 4th, x to the 6th, x to the 8th, x to the 10th. They all look like u's of varying steepnesses. And then all the odd powers, except for one, look like S kind of curves. So x cubed, x to the 5th, x to the 7th, x to the 9th, x to the 11th, x to the 141st. They all look kind of like this, except steeper, depending on how big it is. All of these curves, right? They all look like this, right? 2 to the x, 3 to the x, e to the x. They all look like this. Okay. These functions behave differently because different operations are being performed, right? Different aspects of these functions are changing as x changes. And so when we take the derivative, measuring that change is going to have to be measured in a different way. So just a heads up that even though there's an exponential operation happening here and happening here, we take the derivatives differently because they're different types of functions. So just watch out for that in general.